Hi, everybody. My name is Malik, and today I'll be giving a presentation on organic chemistry's implication in drug synthesis. Oh, geez. There we go. So I have 5 objectives that I'll be discussing. First, I'll talk about my article of choice and how it relates to what we learned in this year-long organic chemistry course. Then I'll be going into more detail about how organic chemistry relates to a topic of interest for me, which happens to be drug synthesis, pathophysiology, and anything about the human body. So as you can see, we'll be talking about aspirin, then Tylenol, and then penicillin, and then I'll finally go over some brief drugs that I found interesting. So starting off, I chose an article called The Symbiotic Relationship Between Drug Discovery and Organic Chemistry. As a brief summary, it discusses the intro to organic chemistry concepts such as polar solvents and basic lab techniques, then getting into more involved in, difficult parts of organic chemistry, such as predicting major and minor products, reaction synthesis, and much more. I picked this article because I felt it did a good job at bringing up topics that we not only learned in Chem 421, but also in Chem 420. And it discussed how the process of drugs are made, such as like experiments it's created, how they're executed, and how the purity is checked in qualitative analysis while using GC and HPLC, which we use quite a bit this year. Moving on, we get to our first drug of interest, which is aspirin. So I've taken the liberty of drawing out the reaction mechanism of how aspirin is synthesized, which we had the opportunity to learn about in Chem 421's lab. And maybe in my free time, I'll end up making some over the summer, although I highly doubt it. So aspirin is commonly used for fevers because it's an antipyretic, which means that it is also used for pain. I won't go into any detail about those because one thing I wanted to mention was that it had blood thinning capabilities, which is used for blood clotting prevention. Blood clots often occur due to formation of fibrin nets, which catches and clumps platelets and red blood cells, forming a blockage and then ultimately resulting in a clot formation. Later, in order to do this, aspirin binds to a specific enzyme, which makes platelets and red blood cells less sticky, which is thus reducing the possibility of clot formation. And this makes aspirin a decent drug to use for things like a stroke or a myocardial infarction, which is more commonly known as a heart attack. I do have one more thing that I want to say about aspirin is that it has been linked to Ray's disease. So if you're under the age of 18, I would not recommend taking it because that's usually where the Ray's syndrome comes from. It's commonly found in teenagers and in kids. Up next, we have Tylenol, which is a common NSAID or non-steroidal anti-inflammatory drug that's used for minor aches and pains. That can include things like headaches, arthritis, back pain, menstrual cramps, and muscle aches. However, unlike aspirin, it's not a blood thinner, which means that it can be used as a post-surgical drug. I'm sure that if you've had any kind of surgery or more commonly a wisdom tooth removal, they have prescribed you probably ibuprofen and Tylenol afterwards, and maybe a little bit of tramadol. So while aspirin can be prescribed post-surgically, it's not commonly prescribed because it leads to longer time for the wound to heal, which can cause an increase in chances of something going wrong, like infection, blah, blah, blah. Since Tylenol is not a blood thinner, that means that it can be given at the same time as other blood thinners like warfarin, which means that it can be used to treat pain and the warfarin can be used to thin the blood. Although I do think that it should be emphasized that you should read the drug labels of what medications you're taking because acetaminophen is very common in a lot of drugs. So I've put let me see, right here, hold on, sorry. Right here, I've put a link that goes to a website that explains a large amount of common medications that have acetaminophen in them, just because it's very common for people to take NyQuil at night so that they can sleep, and then they take Mucinex because they're sneezing all day as a congestant or decongestant, and then they take Tylenol for their headache, and that can lead to some serious problems such as acute hepatitis or liver toxicity or even liver failure if that pattern occurs chronically. So, just please keep that in mind. Now we move on to penicillin. Penicillin is a naturally occurring drug derived from the fungi Penicillium. However, because people have been kind of irresponsible and don't seem to care about antibiotic resistant, we now have moved to more synthetic versions of penicillin, such as the ones that are listed up there. Although it's not just penicillin, most of the antibiotics are actually semi-synthetic versions now. Penicillin is a beta-lactam antibiotic, which is a categorization of antibiotics. However, most beta-lactam antibiotics target the cell wall of bacteria in order to kill off just the bacteria. To explain penicillin's mechanism of action, we need a little bit more background on the bacterial cell wall. So I drew a little bit of a diagram. So I'll bring up my laser here. Up here, you can see a typical bacteria, and you can see the cell wall right here. Now, if we zoom into the cell wall, basically there is a lysine end right here and a serine. So you have an OH group, and then you have an NH2 group, and these are sharing this hydrogen via a hydrogen bond. So what happens is, if you go over here, you have the formation of an ester bond, which we've learned about. And if you look at this last arrow here, you can see the crosslink formation. This crosslink formation is essentially what gives the bacteria its strength in the cell wall. So when this transesterification is broken and the lysine and the serine reform, that means that the crosslink formation has occurred. Now, if we look at the penicillin part, I showed it in yellow just so that it's easier to see. I forgot the oxygen right there, but pretend that there is one right there. You can see that right here, this OH group, the oxygen covalently bonds to this carbonyl group on the penicillin. And once it's bonded, it's like it doesn't unbond, which is why there's no crosslink formation. Because a crosslink formation forms, you have your transesterification, and then these two need to unlink so that there can be another amino acid that forms a link, and then you can have a renewal of your OH and your NH. But when you bind with penicillin, it covalently bonds, which means that there's no cross-linking, which causes the bacterial cell wall to weaken. Now you may be wondering, how come it doesn't hurt human cells? It's because our human cells do not have cell walls, so there's no cross-linked formation to be inhibited. So we've gotten through all of our boring stuff, so now let's get on to some of the more fun drugs. Meth. As we know, there are almost always multiple synthesis routes to make a compound. In this case, there are multiple ways to make methamphetamines, but the method I'll be talking about involves the Birch method, which was the primary way of synthesizing meth by the Nazis back when they were relevant. But how can this be so simple and easy, you ask? Well, I wasn't sure if I should write out the reaction mechanism because I don't know if I'm currently on a watch list or not, but essentially the Birch method uses a sodium or lithium metal in the presence of an anhydrous ammonia to undergo a Birch reduction and change pseudoephedrine into methamphetamines. Now, if we take a look at both of these structures, we can see the resemblance between them. The top structure is pseudoephedrine, the bottom structure is methamphetamine. The only difference here is that the top structure, the pseudoephedrine, has a hydroxyl group. This is why whenever you go to the pharmacy and you want to get Sudafed, like the actual Sudafed, not the generic brand, you need to give them your driver's license or some form of identification so that they can keep track of when the last time you bought Sudafed was, how often you're buying it, and how much you're buying it. So just something to keep in mind. Anyways, here's the reaction mechanism for creating meth. You can see we have a radical formation, which we've discussed in Chem 421. Then the hydrogen from the anhydrous NH3 is taken to form a reduction of the OH group. Looking at this, we also could reduce this OH group using H2 in the presence of a platinum catalyst. But amongst other ways, I think that this was the more interesting way, which is why I chose it. And then surprisingly, there was a research article that went over this. So I will put that in my sources cited. But everybody knows how to make meth, so let's talk about one of the starting ingredients for a different pathway. Methylamine. If we start with ammonia and hydrochloric acid, we form ammonium chloride. Ammonium chloride plus formaldehyde is what we need in order to make one pathway of methylamine. So from my research, there are at least two other pathways, but this pathway is not only the easiest, but it's also the most time-consuming. So we start off with our starting reagents, place them in a simple distillation apparatus, which we know about, and heat it to 104 degrees Celsius. The only thing is that if you go over this temperature, it favors the formation of a different ammonium product, which we won't want. So the distillation process results in reductive amination to form methylene imine hydrochloride, which is relatively unstable. When heated, it will turn into methylamine hydrochloride and formic acid. Usually, this formic acid would decarboxylate into carbon dioxide and water, as we've learned in chapter 21, but most formalin solutions are stabilized with about 10 to 15% methanol. So we actually have some decarboxylation that forms the CO2 and water, while some of the formic acid at the bottom here, ignored this part. Some of the formic acid will react to form methanol, or will react with the methanol to form methyl formate. Let's see. Oh, here we go. But the good news about this part is that it has a low boiling point, so it's boiled off early off in the distillation process. But now that we're here, it's going to be heated. Your methylamine is going to be heated for 3 hours and transferred to an ice bath, where it's going to be vacuum distilled to get all the ammonium chloride out and increase the purity of our substance. This process is repeated once again, and then it's boiled at 160 degrees Celsius for a few hours. Then the crude product is dissolved in hot methanol and vacuum filtrated out once again to get out the ammonium chloride. We allow it to crystallize overnight, placing it in an ice bath to increase the amount of crystals that form, which we've seen from our Chem 420 and 421 labs. And then you can have it like that, or if you want just the methylamine, you can neutralize the HCl with a strong base like NaOH to form methylamine, like strictly methylamine, not methylamine chloride or hydrochloride. And then just for informational purposes, if you, for some reason, plan on making this, you should vacuum desiccate your methylamine for a few hours because it pulls water from the air and will react with it and undo everything that you've done. Although that's theoretically, right? That's all I have. I hope you enjoyed my presentation and thank you for listening.